Okay, well, good afternoon or good morning, everyone. Thanks for coming. It looks like a little bit smaller crowd today, but hopefully people will be joining us. Before we get started, just a housekeeping issue. Next week, here in Massachusetts and in I guess most of the other, at least the 48 states, which are contiguous, we go through a turning back of the clock regimen every time this year. So since I have something at 7 o'clock, another teaching engagement on every other Monday, I have to keep that my 4 o'clock time here for doing this. So that means, although my clock will change to now say 4 o'clock, that's where I'll begin. That means, I guess, on your end, we'll be starting at a different time, an hour earlier or an hour later. I always get these things mixed up. But check your syllabus. Um, you should have something like this floating around from Aaron early on. All classes are 4 o'clock Eastern Standard Time, which means we're an hour difference next time we meet. If you have any questions about the timing, just send them. I'm sure she can explain a lot better than I can. But happy Halloween to be to everybody. Massachusetts is a state of one of our cities is Salem, Massachusetts, where the Salem witch trials were held many hundred years ago. So I guess we hold a little bit of history of Halloween. So hope you have a pleasant time Friday night if you celebrate that holiday. But today we're going to talk about statistics, and today we're going to at least introduce the notion of regression. But before we do that, let's just go over the using a mental exercise, the homework questions I sent last time, which were summarizing what we said about basic statistical inference, and maybe in a few cases went beyond what we said, just to see if we're all on the same page. So on your screen now, you'll see the first question that was asked, which says, what is the following is least likely to be affected by increasing the sample size of a study? So in other words, what do you gain by having big studies? We're going to be talking about sample size calculations in the coming week. But right now, just think about what's the advantage of a big study over a small study? What will you gain from that? So big studies are useful. They're more expensive to run. They take more time. But you get something statistically for the price of the big study. And basically, one of the things you do get is that when you look at your measures of association, your risk ratios, your odds ratios, and you build confidence intervals around them, they will become smaller. You get more precision from a large study. It also turns out when you do your test of significance, you have more power for detecting significant associations with large studies. So those are two things that will happen with large. And both of them are reflecting the role of something called the standard error of the estimate. Remember what the standard error is imagine doing your study many, many, many times, each with the same size data set, each with different people, but of the same numbers of people. And each time you measure your measure of association, your risk ratio, your odds ratio, your regression coefficient, that we'll be talking about today. And you write down on a piece of paper all those different results from all those different studies. What the standard error is the variation among those numbers. It's the standard deviation of those different results from different studies. And if the standard deviation is small, or in other words, if the standard error is small, that means your confidence interval is going to be tighter. Your test of significance is going to be smaller. The p-value is going to be smaller with larger studies because you have a smaller standard error. One thing that sample size will not buy you is answer 3. That was the answer to this question. Is that your potential for confounding won't change. If you make the mistake of entering your data set twice into your analysis, instead of having 100 people who you had in your study, you have 200 people. Everyone's going to be counted twice by mistake. Well, when you do your analysis on 200 people instead of 100, your confidence intervals will get tighter, your power, your p-values will get smaller, your standard errors will get smaller. But if you have confounding with the 100-person data set, you're still going to have confounding with the 200-person data set. Confounding doesn't go away just because. That was the answer to the first question. The second one says if you're doing a 2x2 table analysis, say looking at whether spam eating is related to anxiety, like we did last week, and you calculate a measure of association like a risk difference. And I first tell you that when I did a chi-square test on that table, the p-value was significant, less than 0.05. And now you build a confidence interval around your risk difference estimate. And what the confidence interval contains are all those values for the true value for the risk difference which are supported by the data. If the p is less than 0.05, that means the data does not support the null hypothesis. Therefore, the null value for the risk difference should not be supported by your data, should not be in your confidence interval. That means your confidence interval would not likely contain the zero value, because the confidence interval contains the values which are supported by the data. So the answer to this question should have been 1. Erin's scratching her head because I labeled that in the answer sheet I gave her, but I believe that was a typo on my mistake. Okay, next question. Say you're looking at your hospital that you work in. You're trying to describe length of stay of people who were hospitalized for a certain condition. And you're asked to summarize that in a single number. Calculate a number that summarizes, in some sense, the typical length of stay. And you consider 2 options. You calculate the mean, the arithmetic average. You add up all the length of stay and divide by the number of people. Or you rank the people from lowest to highest by their length of stay and find the person who's in the middle of that line, look at his or her length of stay, and that's the median length of stay. How will the mean and the median be related to one another? Well, typically for length of stay data, we have lots of people with similar lengths of stays, because that's how medicine is practiced these days. But typically, we also have a few people who are in the hospital for longer periods of time, some for much longer periods of time. That might be because they're too sick to discharge, or they're waiting for a nursing room bed to send them to a nursing home for follow-up care. As a result, we typically have a few people with longer length of stays than everybody else. Atypical long values will make the mean get bigger. It won't affect your median. In other words, if you line people up by their length of stays from longest to shortest, and you change the person whose longest length of stay from the value he actually had to 10 days longer than that value, the median will stay the same. The only person who's changing is the last person in line, the one with the longest length of stay. He's still going to be the last person in line. More importantly, the middle person is still the middle person. The median won't change. But the mean will be, because the mean is affected by extreme values. So the answer to this question should have been 1. The next question says, which of these numbers best describe the distribution then for a length of stays? Well, you might guess the median would be better to use than the means to describe variation, to describe a typical value, because the median will not be affected by extreme values, the mean will be. Likewise, the standard deviation and the variance are also affected by extreme values. While the interquartile range is the distance between the person who's 25th percentile on the line, the person who's 75th percentile on the line. Those won't change when you add a few people into the line who have very long lengths of stays. So typically when you have skewed data, length of stay data with a few atypical values, long values, medians and interquartile ranges are the best way to describe the distribution of that. So I would say the best answer to this question is the next question was saying, let's suppose you wanted to compare the length of stay data in 2 groups of people. Say people hospitalized in one part of your hospital versus people hospitalized in another. Well, length of stay is a continuous outcome. So you'd want to compare that with an analysis that takes into account the continuous nature of the outcome. That the numbers you assign to people for length of stays reflect both order and distance, meaning 2 people, one who has a length of stay of 5 days, another has a length of stay of 3 days. The person whose length of stay was 5 days was in the hospital longer. The person was there for 3 days. So order is reflected by those numbers. But also distance. The person who was there for 5 days is there 2 days longer than the person who's there for 3 days. And that's the same distance between a person who's there for 4 days and a person who's there for 2 days. So if you have continuous data, you would want to use an analysis that reflects that. And typically, analyses based on things like t-tests and analysis of variance take the continuous scale into account by comparing the average length of stay in one group to the average length of stay in another group. But remember, I said averages are affected by extreme values. So maybe, especially in small sample size data sets, the t-test might be affected by those few extreme values, and therefore would not be a very good analysis to compare a typical